Hey everybody, welcome back. Today is our last new material in Chapter 5, Solution Chemistry. Just when you were starting to get excited and couldn't wait for more, we're wrapping it up. I know, it's terrible. So today's a pretty short lesson. That's good because that'll give you some time to finish off that graphing assignment from yesterday, which is due today as well. So we're going to do a quick review from yesterday's lesson, and then we're going to spend about 10 minutes on today's small topic, and then we're done. Friday, you'll be getting your chapter test and final assignment. And then we move on to acid-base chemistry. We're getting close, you guys. We're wrapping things up. Okay, so quick review from yesterday. 5 key statements, 5 blanks for you to fill in. So first one, solids have higher solubility in water at higher or lower temperatures. Solids have higher solubility in water at higher temperatures. The hotter the water, the more solutes will dissolve for most solids. Gases have a higher solubility at higher or lower temperatures. So more gas dissolves in a solvent at lower temperatures. Cold pop holds more carbon dioxide gas than warm pop. Okay, gases have a higher solubility at higher or lower pressure. Higher solubility at higher pressure. So that would be directly proportional, inversely proportional. So inverse, yeah, believe it or not, that's an I. Inversely proportional. This one is directly proportional, and this one is directly proportional. Okay, polar substances. So if they're polar, they increase their solubility with an increase or a decrease in temperature. They increase their solubility with an increase. So that one is also directly proportional. And the last one, elements have high or low solubility in water. Elements have low solubility. They keep their states. Solids stay solid, and gases stay gases. They do not become aqueous. Okay, today's lesson, equilibrium. What factors affect the solubility of a salt? So yesterday we looked at temperature. We know that temperature, or more specifically an increase in temperature, increases solubility. What about concentration? If we change the concentration and add more solute to a saturated solution, how does that affect its solubility? And secondly, does the solubility change if we add or remove water from the saturated solution? So I'm going to run a little simulation to show you what this looks like at the atomic level. So here we go. So we're adding some, we can call it sodium chloride, NaCl. Right now that solution is not saturated. There's room for more crystals, so we add more crystals. Those also dissociate into their ions. So we add more solid crystal. Okay, so this time it's not all dissociating. Some of it is sitting at the bottom as a solid. So we would say the solution is now saturated or full. Okay, so what if we add some more? Saturated, we're going to try and increase the concentration, the number of moles dissolved per liter. As I add more, can I fit more in? No. It's saturated, it's full. If I add more solid, I cannot get more of it to dissociate or dissolve. If we add more water, you can see the solid is breaking up. So what we're doing now is creating more space for the solid to dissociate or dissolve. So by changing the volume, we can get more solid to dissolve. Okay? So the answer to your question. Now back to here. Okay, so does concentration change when more solute is added? No. If we had 4 moles dissolved in a liter, adding more moles does not get 5 or 6 moles to dissolve in a liter. If it is saturated, it is full. no more moles dissolved per liter. Does the solubility change if water is removed or added? Yes. So if we were saturated at 4 moles per liter, but I add more liters, then I have space to add more moles. So yes, add water, you can add more solute to get back to the original concentration. Remove water and you would lose some solute. It would have to crystallize out. So the concentration will remain constant in both of those scenarios. Add more water, add more moles to keep the concentration the same. Add more solid does not dissolve more because the concentration is saturated at 4 moles per liter. Okay, those are kind of weird ideas. Hopefully those sink into your brain and make sense to you. Okay, so we've already gone through this definition. A saturated solution is a solution in which no more solute will dissolve at a specified temperature. And we say specified temperature because we know that solubility does change with temperature. If we heat solutions up, we can get more solute to dissolve. Okay, so here's one of the key ideas for today. In a saturated solution with excess solute present, dissolving and crystallization occur at the same rate. This is known as dynamic equilibrium. Dynamic equilibrium. So if we look at this example, here's our NaCl solid. If it goes forward, it is dissolving and dissociating into Na plus and Cl minus. At the same time, those two ions can move in reverse and crystallize back into the solid. So you saw that in the little demonstration. I'll go back and show it to you again, that there was solid turning into ions, and at the same time there was ions turning into solid. So let's go to about here. Okay, so if you look at the block of crystals, you will see that it's not the same crystals that are staying solid. Some are dissociating and some are crystallizing, and you can watch it again when this chunk hits. So it's not all the same ions that are in that same solid. They're moving back and forth. Okay, so this is dynamic in that there's movement. That's what that means. Okay, dynamic means movement. Equilibrium means that the forward rate equals the reverse rate. The change is happening at the same rate. Equilibrium, equal rates. Sometimes you'll see an F above that arrow for forward and an R below that one for reverse. So we can say that the forward rate equals the reverse rate of the dissolving and crystallizing. Okay, a little question down here. The solubility of sodium sulfate at 0 degrees Celsius is 4.7 grams per 100 ml of water. If you add more than 4.76 grams at that temperature, you will have undissolved solid at the bottom because it is saturated. Okay, so dynamic equilibrium. An example of that would be if there was a at the movie theater or there's some restaurant that's lined up. So let's say it's a busy restaurant. It's got 100 people inside the restaurant. And there's 20 people lined up outside. So we say the restaurant is saturated or full. There's no space for any more people. But people can enter and people can leave. So if you looked at that restaurant at 6 p.m. and you saw it was saturated with 100 people inside and 20 outside, and then you came back at 8 p.m. and you saw, wow, it's still full. There's 100 people, and now there's 30 people outside, but it's not the same 100 in there. It's dynamic. Some are moving in, some are leaving. It's changing, but the overall concentration is the same. There's 100 people inside that full busy restaurant. So you could use that restaurant analogy if you'd like. Okay, equilibrium. When a solution in a closed system has macroscopic properties that are constant, we say it's at equilibrium. What does that mean? Well, it means when you look at it, it's not changing. Its visible or macro, large visible properties, macroscopic properties are not changing. So in this container, there is a block of solid crystal. If this thing's at equilibrium, if the forward rate is equal to the reverse rate, the solid changes into aqueous and the aqueous changes into solid at the same rate, the size of that block will not change. So you can see it here in the test tube. It will remain constant. So you can observe a solution at equilibrium and recognize that it's reached its equilibrium position when it's no longer changing. Okay, and there it is represented as a nice little dissolving equation. Okay, so we're going to look at an experiment here and then we're going to wrap it up. So this one's a bit of a brain buster. Let's take a look at it. We're going to focus on test tube A for now, each time. So what they've done in test tube A is it is saturated or full, and we can observe that because it's got this pile of solid iodine, which is becoming aqueous, but at the same time, the aqueous is becoming solid. So aqueous becomes solid and solid becomes aqueous, moving back and forth. And for this experiment, they add radioactive iodine. And the radioactive iodine is glowing gold. So you can see it all here. And I'm just drawing some more gold around it. So as it moves in and you look at it, it falls to the bottom as a solid. So here it is. We've got our solid radioactive iodine. Over time, the solution also becomes radioactive. How is it possible that the aqueous part became radioactive? Because of this. The solid became aqueous and the aqueous moved back to solid. So because it's dynamic or moving back and forth, we can see that evidence with the radioactivity. So the radioactive crystals show us that this equilibrium was dynamic, moving back and forth. Okay, experiment number 2. So now we're going to look at test tube number B. This time they're adding radioactive solution. So the aqueous part is radioactive. So over time, you can see that now this is all radioactive, the solution. But the solid is not. However, if you leave it long enough, you can see the solid also becomes radioactive. How did that happen? The aqueous moved into solid, and then some of the solid moved back into the aqueous. And again, it was dynamic equilibrium. So this little experiment shows you how aqueous and solid are constantly moving back and forth between those two states in a saturated solution, dynamic equilibrium. Okay, that, ladies and gentlemen, is it. Shortest lesson ever. In the words of the great Homer Simpson, woo hoo. That's supposed to be my amazing drawing of woohoo. So practice page 200 in your guide. And this is even more important, these textbook questions. They're a really good way to wrap up the chapter. Really good. And that will help you to get ready for your quiz and assignment tomorrow. Okay? Take care, everybody. And tomorrow, Friday, you can look forward to that quiz and assignment to wrap up solution chemistry.